Good evening all. So we are in the second unit of analysis 2. It is sequence and series of functions. In that we have a subsection uniform convergence and continuity. Uniform convergence and continuity. That means relation between the sequence of functions with the limit function which is continuous there. Okay. Or this all the functions are continuous functions there. Okay. So that is the relation we were seeing. So we have proved the result that if we have a sequence of functions which are all continuous and we have a function f which is the limit function of this, if this function, this sequence of functions converges uniformly to this function f, then we can tell that this function f is also continuous, correct? But in general need not be. If we have a function which doesn't converge uniformly to f, then the function f need not be continuous. Okay, so here is the condition for this sequence of functions to become this f as continuous function. Okay, so that is uniform convergence. So that is the relation between uniform convergence and continuity. So that theorem we have proved, and we have seen some counter examples also there. Okay, so now we have to prove another result, and necessary condition for convergence. Okay, necessary condition for this uniform convergence. Okay, so is that consider a function sequence of functions fn, all the sequence of continuous functions, and k be a compact set. Okay, k be a compact set here. And first condition is this function converges to f pointwise. Okay, this convergence is pointwise. Okay, this convergence on the set K. Okay, and moreover this function f is continuous. This is there, and second point is fn greater than or equal to fn plus 1 for any n on K. So on K, this sequence is decreasing sequence. Okay, this is a decreasing sequence, and each of these functions are continuous functions. Each of these functions are, and your third condition is fn is continuous for any n on K. So these all are there. If there is a sequence which satisfies all these conditions, then this sequence converges uniformly to f on K. So this is the thing we have. Okay, we have to prove this. So how we can prove? We have to prove that fn converges to f uniformly on K. This means uniform convergence. Okay. For that, what we can do is, if you consider Gn as the function fn minus f, then instead of proving fn converges to f, we have to prove that Gn converges to 0. So for computation purpose, I will consider like this, Gn. So Gn is fn minus f. So we will see whether all these conditions are true for Gn also. Then we can do this. Okay. So check the conditions. Gn is fn minus f. We know that fn is continuous function and f is also continuous function because it converges pointwise to f. It's also continuous. Given is this sequence and this function of k. These three are given there. Okay. So Gn is fn minus f. This is also continuous function. Is continuous for any n on k. Okay. So that is true here. Okay. Now, so Gn is a continuous function that we have done, and the thing is we have given that fn converges to f pointwise. That means what? One implies fn converges to f pointwise, so Gn will converge to 0 pointwise. Okay. The thing we have to prove is what? Gn converges to 0 uniformly. That we have to prove. Okay. Right. So Gn converges to 0 pointwise, and each Gn is continuous function. So this we have got. We have used this. We have used this. And what about this? Consider Gn plus 1. Gn plus 1 is fn plus 1 minus fn. Sorry, Fn plus 1 minus f, which is greater than or equal to Fn. So, less than or equal to Fn minus f, which is Gn. So we have got that Gn plus 1 is less than or equal to Gn. That means what? This is true for any n. This implies Gn is also a decreasing sequence. So this is also true. Okay, all these conditions are used for this Gn, and Gn also satisfies all these conditions. Okay, now we shall prove that Gn converges to 0 uniformly. So my claim is Gn converges to 0 uniformly. That means Fn converges to F uniformly. That I have to prove. Okay, so for proving this, for any n in natural number, I will consider some set called Kn. Kn is the set which is set of all elements from K such that Gn of x is greater than or equal to epsilon. Okay, epsilon is some number given, so let epsilon be greater than 0 be given. Okay, epsilon is given. So with that epsilon, I can do this. Okay, I'm considering a set for any n. For any n means we will have Gn also. Correct. Gn is there for any n. So we have this Gn of x is greater than or equal to epsilon. But what is this? Gn of x is greater than or equal to x means x is greater than or equal to Gn inverse of epsilon. Correct. That means this whole set can be written as Gn inverse of, what is this actually? Epsilon to infinity. Gn of x is greater than or equal to epsilon. See, epsilon is there here somewhere. We are taking all the elements greater than that. Okay, that means what? Epsilon to infinity, epsilon is included there. So this is nothing but Gn inverse of the interval epsilon to infinity. Okay, this is your Kn. Inverse image of this set. Okay, but what is this set? This set is a subset of R. Moreover, closed subset of R. Closed subset of R. Correct. This is a closed subset of R. So Gn is a continuous function. Gn is a continuous function. So we know that inverse image of closed set is closed. Inverse image of open set is open if that function is continuous function. Okay. If and only if condition. Okay. So this implies Kn is also closed. Okay. Kn is closed and closed subset of what? Closed subset of K, because all the elements are from K. So Kn is a closed subset of K. And what is K? K is a compact set. So closed subset of a compact set is compact. So Kn is also compact. Okay. So we have got some condition for Kn with respect to Gn. Okay, Gn is included there. Okay. So now Kn satisfies Kn is contains Kn plus 1. Okay, it is sequence of set. Okay, here it is a sequence of functions. Here we have got sequence of set with respect to sequence of functions. Now that sequence of sets has some property, that is each of the set is compact and Kn contains Kn plus 1. That means it is also a decreasing sequence there. Okay, that means how it will be. If you have this is Kn plus 1 will be this, Kn plus 2 will be like this, and so on. Okay, so that is what this. How to prove that? If you take some element from Kn plus 1, then what is this? Gn of x is Gn plus 1 of x is greater than or equal to epsilon. Gn of x is greater than or equal to epsilon, and we know that Gn of x is greater than or equal to Gn plus 1 of x by this. So this is greater than or equal to epsilon. That means what? Gn of x is greater than or equal to epsilon, which implies x belongs to Kn. So Kn plus 1 is contained in Kn. That's what we have got this. Okay, this is one property. Next property is Also, the intersection of all these sets from 1 to infinity is an empty set. Is an empty set. How to tell that? Empty set means how to tell. If it is not empty, then we have to get some contradiction. So if it is not empty, if not, then there exists x belongs to this intersection. Okay, this intersection. So x belongs to that intersection means we know that x belongs to Kn for any n. Correct. X belongs to Kn for any n. Right. And what is this? X belongs to Kn means x belongs to this. So x satisfies Gn of x is greater than or equal to epsilon. This is true for any n. This implies this can be written as Gn of x minus 0 is less greater than or equal to epsilon for any n. This says that your Gn doesn't converge to 0. Correct? Because Gn of x minus 0 is less than epsilon for any n greater than or equal to some stage means we are telling that Gn converges to 0. But here we have got the negation of that statement. So this says that Gn doesn't converge to 0, which is a contradiction to this. Gn converges to 0. Okay, so this is not possible. Therefore, this intersection is empty, and we have Kn is a decreasing sequence. These two properties we have. Okay. Now we have to go to that. Okay. So Kn, this is empty means what we can conclude? There exists some n such that Kn is empty. If this intersection is empty means at least one element should be empty. Correct. So this will be that n. You can take this as some capital N. Okay. Kn is empty. Kn is empty means this K capital N is with respect to this capital N is empty. That means what? There is no such element satisfies this condition. That means it satisfies the other way. For this n, Gn satisfies the other way. That means less than epsilon will be there. Okay, Gn of x is less than epsilon. Correct. This set is empty means there is no such x which satisfies Gn of x is greater than or equal to epsilon. That means for every element in K, Gn of x will be less than epsilon. This is true for every x in K. But we know the property of Gn. Gn is a decreasing sequence, correct? So Gn of x is greater than or equal to G capital N of x less than epsilon for every x in K. And what is this n? For any n greater than or equal to n, Gn is decreasing sequence, correct? Then this implies Gn of x is less than epsilon for every x in K and n greater than or equal to n. Also, this can be written as mod Gn of x minus 0 is less than epsilon for every x belongs to K, n greater than or equal to n. This is the definition of uniform convergence. So this implies this sequence Gn converges to 0 uniformly on K. That means Fn converges to F uniformly on K. That's all. So this is the thing we need to prove. So hence this is proved. Okay. So this is your necessary condition for uniform convergence of sequence. Okay, of a sequence of functions on a compact set. Okay, this is important thing. Compact set we have used everywhere. So there is something important about this compact set. What happens if you remove this compactness? In the whole theorem statement, just remove this compactness. Okay, then we have to get some problem there. So that problem what problem we get is, consider the interval, consider some set which is not compact. Okay, I consider this open interval 0, which is not compact. Okay, and sequence of functions as 1 by nx plus 1. Okay, previously we have told something about this in uniform convergence. Okay, that you go and recall it. Here we have to see whether this satisfies all those conditions. Okay, Fn is a sequence of functions that is there on compact set, that is, on some set 0, 1, it is not compact. Okay, and Fn converges to F uniformly, pointwise. So this converges to 0, that we know on that set. Okay, and it is a decreasing sequence. Okay, that you can check it. Take take the denominator, that will be less than or equal to, and if you take the reciprocal, greater than or equal to. Okay, and each of this is continuous, that is also there, but this doesn't converge uniformly to 0. Okay, that we have proved in uniform convergence. While doing uniform convergence, we have proved that this sequence of functions doesn't converge uniformly to 0. Okay, so we have got a sequence of functions on non-compact set which doesn't converge uniformly to some function. Okay, so this compactness is important to be to these functions to converge uniformly on that set. Okay, if they should converge uniformly, necessarily it should be compact set. Okay, so there is a necessary condition for uniform convergence of this. Okay, that's all. Okay, so next class we can see about some class of functions there. Okay, we just go through this and go back and recall all those things which we have done before, from the starting of sequence and series of functions, and till here you complete those things and keep, then later we will see. Okay, thank you.